we finished GAN last time, and now we're going to get into the variational autoencoder. And this is somehow the place where you can take the generative AI quite seriously. So the dominant models that we have right now, they are basically working with the aid of this variational inference, which ends up with having variational autoencoder. This is the basic architecture, or diffusion model, a more advanced one. And these are the two things which nowadays many people talk about them. So I hope by now you do know that they are not the only ways of generation, of course, but they are quite powerful, especially when it comes to modalities like visual modalities. So today's lecture, we are going to talk about mostly variational inference, and it's a bit more statistical this time, but I try to keep the track that what we are trying to do. Once we understand variational inference, then we can easily design the variational autoencoder, which some of you might have heard, might know about this, especially those who had the deep learning course. In the deep learning course, I promise you that this is not what we had in deep learning is not really what variational autoencoder is. So it was a kind of dummy explanation of variational autoencoder. In this chapter, you're going to understand really what variational autoencoder is. And you really need to understand variational inference for that. But this is not the only thing that we're going to learn. Once we understand this framework, we can also develop other models. Diffusion model is going to be the dominant one, which we're going to do in the next chapter. But this also gives you like a very powerful tool that you can even develop your own model. So it's somehow like, adversarial networks, like it's a kind of paradigm or framework for generation. This is also another one. So let's just start with the idea. So one quick recall. So we are right now working with modern generative models, right? So we talked about the two, like a rough separation between two kinds of ideas. The first one was the idea of explicit distribution realization. So we wanted to learn the distribution explicitly, and then we use that distribution to sample. So we had lots of troubles there, but especially when we wanted to do something autoregressive, that was a good way to go, right? And there are also implicit approaches, which we call the modern approaches. The first one was GAN. GAN was essentially sampling latent, pass it through one neural network, you get something at the output, then you put something called discriminator. It's another neural network. That's going to help you to compute some gradient to train that generator, right? And then when you keep on doing min-max game, at the end of the day, you're going to have your generator trained such that when you sample one Gaussian latent noise, and you pass it through the generator, you're going to see a data sample, right? So that was the idea of GAN. And this is fitting this general framework that I told you before. So you have some generator network. You sample some latent variable. This is typically a Gaussian variable because this is very easy to sample. Then you pass it through the generator. It's going to give you some data sample at the output, right? So this is the whole idea. When you want to do training, what you're going to do, you're going to do implicit maximum likelihood. So implicit maximum likelihood in GAN, it was simply the min-max game, right? So we did it together. And once you train it, you simply use that architecture, that generator, to generate your sample, right? So this is the general paradigm in all of these three classes, GAN, variational autoencoder, or diffusion. We pretty much do the same thing. The only difference is that we are going to somehow realize this generator in different way. And when we have different way, we're going to have different approaches to train it. Okay? So now, the generator in general in these architectures, as we talked before, is going to always take a sample from the latent. It's going to process that sample. It's going to give us the data sample, right? So GAN was basic in the sense that this generator was a specific neural network, right? So it means that when you get the sample, which is the latent sample, and you pass it through the network, at the output of the network, you already have your data sample, your image, for instance, right? That was GAN. This is what I call it a deterministic generator, right? Because the generator is a deterministic function specified by the neural network, right? But I can do that also probabilistic. Can you think about a probabilistic way? So we're going to do it together, okay? So one point that you should pay attention, GAN is limited. Typically, the things that we train are limited to deterministic generator, right? This is a neural network. You're going to get one sample from Gaussian distribution. You're going to give you sample from data, right? But we can do it in a probabilistic way. What do I mean by probabilistic? I mean the whole process that is taking our latent sample into a data sample, it does not need to be a deterministic function, right? It could be probabilistic, right? It could be a stochastic process, right? Now, if we want to do that, we have different solutions. The most basic solution is to somehow try to replace or somehow use this kind of model to make a kind of a stochastic process from z to x. So let's see how we can do it. Say I have this neural network, this computational model. This model is able to see one latent sample, z, and then it's going to compute for me one output mu, okay? So any z that I give to it is a neural network. It's going to give me one output mu, right? So in GAN, this mu was literally our data sample, right? But I can think that this mu is essentially a statistic of the distribution which is giving me the data sample. So for instance, I have this neural network. It computes for me this mu. Then I have this distribution p. This distribution p is parameterized by mu. And don't worry, I'm going to give you an example. So this distribution p is parameterized by mu. So I'm going to put this mu value that I computed inside that. And now I have a distribution on x, right? And I sample from that. Clear? So I'm going to take that mu, I put it inside that distribution. It's going to give me one distribution. I can press the button and generate one random sample from that distribution, right? That output x still is coming from z, but it's not deterministically computed from that z, right? It's computed by a stochastic process. Everybody's clear? Questions? So you got the idea? My model is computing this statistic, this mu. This mu is going inside one distribution. It's going to specify the distribution. Now that I have the distribution, I'm going to generate one sample from that distribution, right? Now, what I can think of, I can think from z to x, I still have a process, right? And that process is not anymore described by a deterministic function, but it's described by a conditional distribution, right? So I could say that this x is distributed with this distribution p of x with parameters mu. That mu is specified by z, so I can say that x is essentially distributed with some model, right? Or some, say, parameterized distribution given z, right? So I specify z. When z is fixed, the distribution is fixed, and then I can sample from it, right? So it's a kind of conditional generation of x for a z, right? So essentially, you think from from z to x, all of it to be one conditional distribution, which is described by that model g and that distribution p, x, and mu. Okay? Everybody's cool? So, example. Let's consider one example, the best example, which is fitting what we are going to do in variational autoencoders, is the Gaussian case. So let's say that I have one model G. This model G is going to take m-dimensional input, which is the same dimension as the latent. So it's going to get one latent, and it's going to give me d-dimensional output. So d-dimensional is exactly the dimension of my data. Okay? Now, I have this G, this neural network. When I give some latent Z to it, it's going to give me one mu, which is d-dimensional. So I'm going to compute mu for any Z. When I want to just generate one data sample, I'm going to first generate or sample one latent, right? And then I'm going to give this latent into this neural network. It's going to give me a d-dimensional mu. But that mu is not my data. I'm going to treat it as the mean value of a Gaussian distribution, right? So I'm going to write down my distribution to be P of x and mu. This is the distribution that is parameterized. To be a normal distribution with mean mu and variance 1, identity variance. Okay, everybody, every entry of x is distributed with variance 1, all of them independent. Okay? Now, I have this distribution, mean mu, variance 1. I can now simply sample from that, right? Correct? And that sample is going to be my data sample, right? So mu, which is computed based on z value, the latent sample, is not giving me the data sample, it's giving me the mean value for that distribution, right? Everybody's clear? Okay, so one thing that you should pay attention here is that this kind of generation is not very hard for me, right? Because everybody agrees if I have this distribution, which is a Gaussian distribution with variance 1, I mean identity variance. This is very easy to sample. Everybody agrees? Do you know why? Can you explain me why? Like those dummy questions we had in the exam? Justify your answer. Any question? Anybody can explain why this is easy to sample from this distribution? Important thing? I know it's a Gaussian distribution, that's one point, but there is one other point which makes it super easy to sample from it. Don't be shy, just... Sorry? Not the mean, but the covariance, right? So the covariance matrix, or covariance here, is identity, right? This means that every entry in the dimension is independent, right? So I do not need really to sample all of them together. I just independently sample every dimension, and then I'm going to get one sample that I want, right? So if you have two variables which are independent, you don't really need to sample from any joint distribution, right? So you sample the marginal, then that is a joint sample as well, right? So this is a key point here, which is going to be with us the whole variational autoencoder chapter. So this is an easy thing to sample, not simply because this is Gaussian. I mean, Gaussian distribution is easy to sample, that's right. But it's even easier than a general Gaussian distribution because of the covariance. The covariance is identity. That is very important. So I have this neural network computing the mean. I have this parameterized distribution to sample from. This is going to be the whole generation for me. And I can say that from x to z, this is my data sample, this is the latent sample, I have such conditional distribution, right? So this conditional distribution, this guy is the Gaussian distribution, right? For x, but its mean value depends on z, right? So this distribution is going to change if I change z, right? And because of that, this is a distribution of x given the value of z. So when you change the sample z, this distribution is going to change, right? It's a conditional distribution. It's not a marginal distribution. Everybody's cool? Okay, great. So we can extend this guy. So we can think of a more general case, again Gaussian, but this time instead of simply learning or computing the mean value by the neural network, we can compute mean and covariance, right? That is also possible. So I can say I have a neural network which is taking one latent, m-dimensional latent, and it's going to give me one mean and one covariance matrix, right? And then every single latent sample that I have, I give it to this neural network. It's going to give me the mean value and the covariance matrix. Then I'm going to sample from one distribution with the same mean and covariance matrix, right? This is, again, a conditional generation of x given z, but we should always pay attention. This is not deterministic anymore, right? I cannot write down a function which takes z and gives me exactly x, right? I can only explain what is the distribution of x given z, right? Everybody's cool? So this guy is, again, not that hard to sample, but given that I have a covariance matrix sigma, then this might be a bit more computationally expensive as compared to the other one, right? Because I need to correlate the samples and the entries inside the sample, right? So if you like to just check how you can do it. I mean, just spoiling alert, you can use SVD, right? You can sample from IID and then use SVD to make it correlated, just to give you a hint. But if you are interested, just take a look. But at the end of the day, you still can sample from this distribution with just cubic complexity. OK. So again, here what I can say from x to z, from z to x, I have this conditional distribution. So once I have z, I have the mu value, I have the covariance, and I can put it inside the expression for the Gaussian distribution. And this is going to be the distribution of x when z is known, right? And as I change z, this distribution is going to change. So this is a conditional distribution, not a marginal, right? OK, cool. Now, if you want to think in general about a probabilistic model, what we can say, so we usually call it latent space probabilistic generation because we first start with a latent sample, and then we pass it through some sort of stochastic process to generate the sample. So the way that we can do it, we first always sample from the latent space. Now this latent distribution is totally our choice, right? Z distribution is my choice. I can put it anything that I want. Typically, we'll put it something that we can easily sample, right? Like IID Gaussian. That is easy to sample. Or IID uniform. And then next thing is that we compute some sort of statistics using a deterministic model, a neural network, some computational model. Now that we have this output, this is statistic, we are going to use one parameterized distribution to specify the conditional distribution of the data, and then we sample from that conditional distribution. And again, we typically consider this conditional distribution to be something that is easy to sample, right? Again, like a Gaussian. Most of the time, we just do Gaussian. Everybody's clear? Questions on that? Now, do you think this is a kind of feasible way to generate data? So computationally thinking. Is there any challenge that we might have here? If I want to sample from it, is it a hard thing to sample from? No. Yeah? If I put these guys to be simple things, z and the conditional distribution, it's not hard to sample from, right? So let's just look at it together. So if I want to generate by this approach, I first need to sample the latent, right? If I want to sample the latent, I can put the latent distribution something easy. Most of the time, almost all the time, we're going to set it to be Gaussian, right? This is why in any generative model you start from a Gaussian noise, right? You put it to be IID Gaussian, you sample from that, so this is very easy to sample, right? This is IID Gaussian, you need to just sample, say z is dimensional m, you need to just sample m independent Gaussian variables, that is quite easy, and then you just have your noise, right? Now that you have this guy, the next thing is to just compute this statistic. This is a forward pass over a neural network. This is again fine. The last thing is to just sample from the parameterized distribution. That is again a simple thing to do if you set that distribution to be Gaussian, right? Especially Gaussian with variance, covariance 1, right? So if I think about that, and most of the time again we consider this Gaussian distribution. This is easy to sample. All of it is computationally feasible. So I can simply do it by my computer. Yes? So that is no problem. But one thing that might come to your mind is that, that point. So as long as I put all these two distributions, the prior distribution of the latent and this conditional distribution to be some easy to sample distribution like Gaussian, I am fine. But one thing that might come to your mind is that, well, this is computationally easy to do, but at the end of the day, you're ending up with some Gaussian distribution, right? But you are going to mimic some data distribution, which is supposedly very more complex than a simple Gaussian distribution, right? So, do you think this is really the case? Do you think that we are taking samples from a Gaussian distribution? Actually, no. We are not taking samples from a Gaussian distribution. We are taking samples from conditionally Gaussian distributions, right? And then the data distribution is not necessarily Gaussian. I mean, actually, it's not Gaussian at all. Do you see what I'm saying? If you don't see it, just take a look at this example, okay? So, consider this example. Say everything is a scalar, okay? Latent space is a scalar, data space is a scalar as well. Say I'm starting with one latent sample, which is a uniform sample. So I just sample the uniform distribution between 0 and 1, quite easy thing to do. Now that I sample this one, I am going to pass it through this neural network. This is a very dummy neural network. This is just one thresholding, right? So it has one parameter theta, which I can tune. And it's going to look at that uniform distribution, uniform sample, and then it's going to compare it with theta, right? If it's less than theta, it's going to return 0. If it's more than theta, it's going to return 1, okay? So Z is my latent. This G, or this thresholding, is actually the neural network, which is computing this statistic for me. And now I want to generate my data. What should I do? I'm going to take this statistic, I put it inside a distribution, I sample from that distribution, right? So I told you we do always Gaussian. Let's do Gaussian, okay? So let's say that I put one Gaussian distribution, P of x and mu. So P of x and mu is simply a Gaussian distribution with variance 1 and mean mu, okay? Now, the conditional distribution of x given z is essentially one Gaussian distribution, and its mean value is exactly the output of this threshold, right? Which depends on theta. If I change theta, it's going to change. But it is not only depending on theta, it also depends on the sample z that I have. If I change z for a fixed theta, this is going to change as well, right? So that guy is the conditional distribution of x given z, right? But what if I want to know the data distribution, which is the distribution of x only, not x given z? What should I do? Marginalization. Great. So I'm going to do marginalization. I'm going to say I have this conditional distribution. I'm going to multiply it with the latent distribution, right? And I integrate it over latent, right? Now, I have this guy. This is the model that I set. I have this guy. This is my choice, right? I started to sample from some uniform distribution. So I'm going to put my choice here. And I have everything that I need to compute the data distribution, right? So let's do it for this example together. So I want to compute this guy. My z value is only changing between 0 and 1. So I'm going to limit the integral between 0 and 1, right? Good. Now, if I open this guy up, first of all, this pz is essentially 1 in this interval, right? This is a uniform distribution between 0 and 1, so the density is 1 everywhere, right? So it's going to be in this form. And I also replace this conditional distribution like this here, right? Now, looking at this guy, if my z value, so if I first look at this interval between 0 and 1, if I look at the interval between 0 to theta, what's going to be the value of mu between 0 and theta? If z is between 0 and theta, what's going to be the value of mu? 0. It's going to be 0, right? So I can say that when I am taking the integral from 0 to theta, this guy is 0. Doesn't matter what the z is, right? And when I am in the interval theta to 1, what's going to happen? This is 1, right? So this is going to be the second one, right? Now, I can compute these integrals, right? Because essentially the integrand does not depend on z, right? So the integral of the first guy is going to be simply theta times whatever the integrand is. Here, 1 minus theta times the same thing, right? So it's going to be, at the end of the day, this guy, right? So it's average of two Gaussians. One of them is at 0, mean value 0. The other one is at mean value 1, right? So is this distribution Gaussian anymore? No, it doesn't look like a Gaussian. Of course, it consists of Gaussian components, but it's not a Gaussian at all, right? Everybody's clear? So this is what we call it, a mixture of Gaussian distributions. And mixture of Gaussian distributions are actually a very powerful thing, because intuitively, if you just mix lots of Gaussians together, then you're pretty much capable of making any weird distribution, right? So that guy is not anymore Gaussian. This is very strong distribution, right? Very rich set of distributions, right? Now, if you want to look at this particular guy here, so this is our data distribution, right? And what is the model parameter here in this expression? What is it? Theta. This is only theta, right? And I can play with theta to change my distribution, right? Now, let's look at it together. Say this is the distribution at 0. So this is the Gaussian distribution with mean 0. This other one is the Gaussian distribution with mean 1. Now, if, say, for instance, theta is half, so I'm going to have half of the first one plus half of the second one, right? So this is going to look like this, right? You're going to have two picks, right? Now, I could, for instance, give value of, I push theta to have more weight at 0, right? It's going to look different, correct? If I push theta to have more value at 1, so for example, I set theta to be 0.1, then it's going to look more like a Gaussian distribution at 1, but it's still a bit, deformed, right? So in general, when I play with this theta, I can just have lots of distributions in between, right? And I can do it with only two Gaussians. You can think if my latent space takes more cases, it's going to get richer and richer, right? Everybody's clear? So that is the main idea, that this kind of Gaussian generation, conditional Gaussian generation, is not going to limit us in terms of the kind of distribution that we are realizing at the end of the day. So if you want to think of a general case, in general case you have one conditional distribution, which, as I told you, you most of the time consider a Gaussian. And then this means that for any value of z, so z value here is actually specifying the mean value of these Gaussians, right? For any value of z, you're going to have one Gaussian at different point, right? And then the data distribution is actually the average of these distributions with respect to the distribution of z itself, right? Because you're going to get each of those guys, each of these Gaussians, right? And then you multiply it with the distribution of z at that particular point. And you add all of them up, right? So it's going to be an average of lots of Gaussians, right? So for instance, if you think of a Gaussian prior for your latent, then it means that every single guy here, this guy, is going to get multiplied with the probability or the density at that point, right? And then you add everything up together. And you're able to somehow make any distribution that you want, right? Because you have lots of Gaussians, and you can play around with the places of those Gaussians. And because of that, you pretty much can realize anything that you want. Everybody's cool? No? OK, so this is what as I told you, this is what we call it Gaussian mixture distribution. And Gaussian mixture distribution is somehow a kind of same thing as the neural networks are when you want to realize a function, right? If you have a neural network and you make it deep enough, then you can pretty much realize any function. If you have lots of Gaussians together, and then you mix them, give lots of parameters to mix them, then essentially you can realize any distribution that you want, right? This is what we call it universal approximation or universality of Gaussian mixtures. What I put here is quite informal because like there are lots of mild conditions that need to be satisfied for the distribution. But what we can say that if I have this conditional distribution Gaussian, and I have any prior, so it really doesn't matter what the prior is. Okay? So of course for some priors it's going to converge faster, but in general this prior PZ is not really important. As long as I have this Gaussian guy here, and that mean value that I'm computing is computed by some, say, deep enough neural network, then I am able to pretty much approximate any distribution with this mixture of Gaussians. Okay? So this means that if I have this guy, now, I mean, say a formal statement is that this PW is essentially explaining or representing a dense set of distributions, but you don't really need to think about this terminology, dense set of distribution. What you can say if you have any distribution Qx, right? And Qx could be your data distribution. Any complicated distribution that you have, you could say that there exists one choice of value W, so one choice of parameters for your neural network, which is computing the mean value of that Gaussian distribution. Such that this marginal distribution of X is approximately the distribution that you are looking for, right? And this is a very strong statement, right? So it means that if I do what we did in the previous slide, so we just put a neural network to compute the mean value of the Gaussian, right? And then we sample from the Gaussian conditionally using that mean value. The output is marginally distributed with any distribution that you want, as long as you have the right choice of the neural network, right? So this is a very strong statement, right? And as I told you, like what I told you here is quite intuitive, but you can take it with a good amount of approximation. Yeah, question?
So, intuitively, why the PZ doesn't matter?
Why the PZ is not really important? Yeah, because essentially you can play with this W in a way that, I mean, of course, if PZ is, there are, as I said, there are a bunch of constraints. So Z, for instance, if you think of Z to be like any point inside your space, right? So PZ cannot be uniform anymore, right? Obvious, right? So it should be some decaying distribution, right? But how it decays, it does not really matter. Even if it's sub-Gaussian, it's still okay. Because at the end of the day, you just need to play with the place of those Gaussians, right? So say you have bunch like a envelope with lots of weights, right? So if that envelope is Gaussian, then you put a couple of Gaussians which are proportional to those weights, right? But now if you change the envelope, that distribution PZ, then the weights are going to change, but it doesn't matter. There is one other point which is exactly the weight that you had in the previous envelope, right? And you just need to push that Gaussian towards that one, right? So you just need to play with the place of those Gaussians. So one simple thing that you can think of is that if I have, say I have two Gaussians, this guy and this guy, and now these are the conditionals, right? And then I have this distribution as PZ, right? At the end of the day, the thing that is happening, the weights are these two, right? These are the weights that I am going to add these guys, right? But say instead of this one, I have this distribution, right? For Z, right? Now, this value of the weight with this one is happening here, right? So I can just shift this guy to be here, right? So I don't really need to play with PZ anymore. I just play with the place of the Gaussians, right? But of course, depending on PZ that you choose, that neural network that is computing the mean value for you has a different power, right? A different strength. But it's not important when you think asymptotically, like you assume like you have super deep neural network, right?
So we can interpret it computationally like PZ is our input and then we pass it
Exactly. So when you fix PZ, then of course you can train W, and then you get the optimal one is going. If you change PZ, then the optimal W is going to change, but it doesn't really matter. At the end, there exists one W that does that job for you. Exactly. It's the distribution by which you are sampling your latent. Right? So, questions? No question? So, moral of the story, what we are doing here by this probabilistic generation is quite a strong way of generating. We can pretty much approximate any data distribution that we want. So it means that if we somehow come up with the right training algorithm, then at the end of the day, we can make this guy to mimic the data distribution, right? And this is what we are looking for, right? So one thing that you should pay attention here is that this is only possible when I am doing conditional generation, right? So I first sample Z, and then I conditionally sample a Gaussian, right? Correct? So you might ask me why you didn't do it at the first place. Like at the very, very beginning of the course, you just put one model for the distribution and sample from it, right? And then train that one. This is not possible because that model needs to be a super complicated model like the energy-based model, which can realize any distribution. Now, I don't really need to do that because this conditional distribution is simply a Gaussian, right? That guy is a Gaussian. Since I'm doing this conditional generation, the marginal distribution could be anything, right? So this way of generating Z first and then condition to that generating X is the trick which is making us capable of realizing any distribution, right? So you should keep this in mind. Don't confuse yourself. Okay, cool. So now that we have the idea how this model works and how we can sample from it or how we can generate something with it, now the question is that can we go ahead and find the right parameters? So can we train it? So any idea if I want to train it, what should I do? The idea that we apply everywhere? Maximum likelihood, right? So I need to use maximum likelihood. I mean, of course, sometimes, like again, I cannot do it directly, right? But I should check what's going to happen if I want to do maximum likelihood. Then I'm going to find out a way to do it either directly or implicitly, right? So I want to just do maximum likelihood. This means that I want to somehow maximize the likelihood computed by this model. So let's say that I have one particular sample X. This is one training sample that I have. I'm going to take this sample, I put it inside the distribution of my model, and then that is going to give me the likelihood of the model. I try to maximize it with respect to the model parameters, right? So if I want to write it down here, I would say, given the probabilistic generation that I have, this guy, this marginal distribution P of X, is the distribution which depends on my model, right? And the model is essentially specified by the parameters W, right? Now the thing that I want to do, I want to put X inside this term, and then I want to compute this probability or distribution, the density value, and that density value is going to give me the likelihood of model W, right? And then I want to maximize this likelihood with respect to W. This is what we have done up to this point all the time, right? Now, if I want to do that, this means that I am going to put the expression for this conditional distribution. I told you this is always Gaussian, so I'm going to put it Gaussian. The mean value of that Gaussian is computed from the latent using a neural network, which is parameterized by W. And then the prior distribution, again, we think of a Gaussian distribution, right? So I'm going to replace that guy here, right? And that C is somehow collecting all the constants of those Gaussian distributions together, right? So I don't care about them. I just take them out. Now, if I want to do that, I mean, of course, there are two exponentials. I can just merge them together, and I need to compute this integral. Do you think this is a kind of feasible integral that I can compute? No. What is the problem here? If instead of GWZ, instead of this guy. I had simple z. Was it still complex? No, you could compute it, right? Using Gaussian integration. But what is making it crucial here is the neural network, right? So that neural network, you don't really know how it exactly behaves, right? It's a deep neural network with lots of weights, right? So this G here is a neural network. It's a very complex model. And essentially, we cannot compute this integral, right? Which means that we cannot compute the likelihood, right? Which means that we cannot train this model. We're back to square one, right? Like always. So you always think that there is a new solution to this problem, but you end up with the same complexity. Yeah, you could guess. You cannot, make a hard problem simple, right? So this integral is not tractable, even though now you're capable of realizing any distribution using this mixture of Gaussians. At the end of the day, it's very hard to compute its likelihood, and because of that, it's very hard to train this model. So everybody sees what is the challenge here? Okay, so this is the key challenge of this kind of modeling, and to resolve that challenge, we do what we call it variational inference. So variational inference is a solution which is trying to resolve this problem. So just to give you the idea, so this is the moral of the story or summary of what we have done up to this point. So we have this probabilistic generator using the Gaussian conditional. This is a very good model because it can pretty much approximate any distribution that we want. This is cool, but the challenge here is that we're going to end up with a likelihood term which is not tractable to compute, right? And because of that, we cannot train this model, right? So if we want to put it, if we want to understand variational inference, it's better that we put it into non-computational context. So what do I mean by that? I can represent the whole problem in this form. So I can think of a statistic problem. I have access to one distribution, PZ. This is my prior latent distribution that we had in our problem, right? I also do know what is this generative distribution. So I know what is P of X given Z. I also have access to that distribution. What I want to compute is distribution of X, right? It means that I want to compute this integral, right? And this integral is not feasible to compute. And not feasible totally, but it's not tractable. It's not easy to compute. Now I want to see, is there any way that I can come up with an alternative approach to somehow approximate or estimate this distribution Px, okay? This is what we do in variational inference.